Hey Dora, let's go to Isaiah the Iguana's house.
Good idea, Boots.
Here's Isaiah the Iguana's house. Where's Isaiah the Iguana?
We don't know.
Should we call him?
Where's the phone?
There's the phone.
Yes.
Let's call him.
Boop, 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 boop.
Ring, ring, ring. Ring, ring, ring. Ring, ring, ring.
Yo, what's up?
Hey Isaiah the Iguana. Where
What
are
is
you?
that? I mean, I'm somewhere out here in these jungles, but I can't tell my position or my momentum. I don't know.
Can we try to find you with our GPS?
I mean, that's cool, yeah.
Alright, we'll call you back. We're using the GPS to find you. Let's turn on our handy dandy GPS.
Wait, we can't get an accurate measuring of his position.
There seems to be some limit, lower limit, on the standard deviation of our measurements of his position. The reason that Boots and Dora can't measure Isaiah the Iguana's position accurately enough is due to this relation called the Heisenberg uncertainty principle. The standard deviation of their measurements of his position times the standard deviation of Swiper's measurements of Isaiah the Iguana's momentum has to be greater than or equal to this limit, which is h bar over 2. So when Swiper is measuring the momentum, he's decreasing sigma p, meaning that sigma x has to grow larger in order to stay above the limit, as a fundamental law of the universe. Therefore, the standard deviations of the measurements of Boots and Dora isn't tiny enough to accurately determine where Isaiah the Iguana is. There seems to be some limit, lower limit, on the standard deviation of our measurements of his position.
I am accurately measuring his momentum. Therefore, by the Heisenberg uncertainty principle, you cannot know his position.
Oh no!
Swiper is observing.
Swiper, no observing! Swiper, no observing! Swiper, no observing!
Oh, man!
Oh, we found him. He's 500 yards that way.
Let's go and get him!
Isaiah the Iguana is too far away. Maybe we can find a scooter.
Let's see if there's one in backpack.
Backpack, 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 backpack.
I'm the backpack.
Yay!
Why don't you see if there's a scooter inside me?
Well, we're uncertain what's inside the backpack. I think there's a wave function for this.
So before Boots and Dora have made a measurement, they don't know what's inside the backpack. And right now it has a likelihood of being, it has an equal likelihood of being a scooter, a ping pong ball, and a fish. And what they want is that it's a scooter. So we're trying to find the probability of it being a scooter. And for that, we have to do the bracket of scooter with the wave function. And we square it to find the probability. And before we do that, we have to find the normalization factor, since the probabilities of all of these has to add up to 1. And right now, the coefficients are 1, 1, and 1, so the probability is actually adding up to 3. And so we have to make this 1 over root 3, so that when everything is squared, it it all adds up to 1. So then when we evaluate this, we get a value of 1/3. So if there's a 1/3 chance of the item in the backpack being a scooter.
And that works.
Aw, this is not a scooter.
Try again. Maybe you'll find something else this time.
No, because we have already found a not scooter, the wave function has already collapsed. That means we can't find a scooter.
Now that Boots and Dora have made a measurement of what's inside the backpack, they know that it's a ping pong paddle. And the wave function has collapsed, so it cannot be anything besides a wave function, besides a ping pong paddle. So now everything else goes away, and it is only a ping pong paddle. So the probability of it being a ping pong paddle is now 1, and it's always going to be 1, and no matter how many measurements they make, it's always going to be a ping pong paddle. So they have to walk to go to Isaiah the iguana.
Shoo!
Okay. What?
Oh no, we'll have to walk to Isaiah now.
Help me, I'm gonna fall through these slits!
Oh no, Isaiah's hanging on the ledge.
We have to save him. He's gonna fall through these slits right there. Double slits.
We should get these couch cushions. How many do we need to save Isaiah?
So Dora and Boots want to know what the interference pattern is going to look like for the probabilities of where Isaiah is going to land on the floor after falling through the double slits, because he interferes with himself since no one's observing which slit he's going through. We can determine this given his mass and a couple of distances involved. So we know that the distance, change in x, from where he falls to the double slits is 2 meters. We also know that the acceleration due to gravity, we'll round it to 10 meters per second squared. We also know that his initial velocity, v sub I, which is the velocity with which he falls off the balcony, is 0 meters per second. From this we can use kinematics equations. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the change in x. The initial velocity is 0, so we can ignore that. So his final velocity then is the square root of 2 times 10 meters per second squared times 2 meters. So this equals the square root of 40, is 2 times 10, meters squared, because meters per second squared times meters per second squared, which is itself equal to 2 root 10 meters per second. So his velocity when he hits the double slits is 2 root 10 meters per second. So using this, we can determine his momentum as well. We know that Isaiah the iguana's mass, because he's really skinny and tiny, obviously, his mass is 3.146134, don't necessarily need these significant figures, but oh well, times 10 to the negative 33 kilograms. So his momentum then is going to be equal to his mass times his velocity, which we found to be 2 root 10 meters per second. When you multiply these out, you're going to get 1.9897 times 10 to the negative 32 kilogram meters per second. So this is his momentum after going, when he gets to the slits. Now, we can, using his momentum, figure out his de Broglie wavelength, which will tell us how he'll make the interference pattern. So the de Broglie wavelength is going to be equal to Planck's constant h over his momentum. So we know that Planck's constant is 6.626 times 10 to the negative 34. His momentum we just calculated is 1.987 times 10 to the negative 32. So when we divide this out, we find that his de Broglie wavelength is going to be equal to 0.03 meters, about 0.03 continued meters. So that's his wavelength.
Last call for
Using this,
Last call for roll check.
we can determine the distance between the higher probability spots on his interference pattern for where he's going to land. So we use this by, the distance between these spots is change in y. We know that this is equal to L times the wavelength over the distance between the slits. The distance between the slits is 0.1 meters. L is the distance between the slits and the floor, which is 3 meters. And his de Broglie wavelength we just calculated is 0.03 continued meters. So when we multiply these all out, we get that the change in y is equal to 0.1 times, 0.03 continued times 3 meters squared over 0.1 over meters. So meter squared over meter simplifies simply to meters. When you do out the, go through this calculation, you'll find that it's roughly equal to 1 meter. So therefore, the distance between the cushions that Dora and Boots have to put down to save Isaiah the iguana is 1 meter, given that he interferes.
We need someone to observe Isaiah before he falls through the slits.
We need someone to see what slit he goes through. Hey, it's Swiper!
What are you doing here, Swiper?
I'm going to observe Isaiah falling through the actual slits, record it at the slit, so that way it collapses the wave function at that slit and there's no longer an interference pattern. That way we only need 2 pillows instead of an infinite amount.
Yay! Before Swiper was observing which slit Isaiah the iguana fell through, the probability of Isaiah the iguana landing at a certain point A on the floor was equal to this value, which is the bracket of that position A with a wave function for a particle only falling through the first slit, plus the bracket of the position A with of the wave function of a particle that goes only through the second slit, and then that entire value squared. This creates a wave-like function for the probability, so that as your change A, the probability will go up and down and up and down and up and down. And this is what the interference pattern is for an object moving through double slits where it's not observed which slit it goes through. However, once we observe which slit it goes through, it collapses the wave function, or the probability of it ending at a certain point, A, changes to this, which is the probability of it ending at a certain point A if it goes through the first slit, plus the probability of it ending at a certain point A if it goes through the second slit. Now this does not create an interference pattern unlike this does. So when we look at where it is likely for Isaiah the iguana to land, we now see that it's a different type of areas of probability. So if we have probability, which I'll just call P, on the y-axis and position A on the x-axis, before we change the probability by observing which slit it went through, the interference pattern created a graph like this, where the middle hump is largest and then this distance was change in y. But now, and this was bad because Dora and Boots only had 3 cushions, and there's many of these spots where it's probable for Isaiah the iguana to land on if it's an interference pattern. So they didn't have enough cushions to accurately protect him, reliably protect him. Now that we measured which slit he's falling through, it changes the graph to something like this, where each of these 2 more probable spots is underneath the each individual slit, and you could see that this hump corresponds to this term in the probability, whereas this hump corresponds to the term with wave function 2 for a particle that went through the second slit. Now we only need to put 2 cushions, and we're able to save Isaiah the iguana.
Now we have 2 cushions.
Oh no, Isaiah's falling!